my first attempt at giving a video talk with something handwritten instead of using the slides, which I like because it looks more like a Blackboard talk. So as I was saying, the talk is going to be about the oriented Plateau problem and the question of Almgren. So you see the title written there. And most of what I'm going to say is actually joint work with Guido de Philippis, Jonas Hirsch, and Annalisa Massaccesi. Okay, so let me start with a very brief description of what is the Plateau problem in the way we are going to understand in this talk. So the initial problem, which was formulated by the Belgian physicist Plateau, consists in the following geometric fact. So take a gamma, which is a curve, which is sitting in the three-dimensional space. And let's say this is a closed curve. So it's going to be something like this. Of course, it's closed, so that one is not there. And then I look for surfaces sigma bounding gamma or bounded by gamma, which minimize the area. Okay, so this is a very famous problem, and one of the first things that you might ask as a mathematician is, what do you understand exactly as surfaces? What does it mean to be bounded by gamma? And what do you understand by area? And all of these three concepts can be more or less general, and depending on how general or how you sort of phrase the problem, you can actually happen to land into different type of relational questions. So let me actually insist on the fact that here I'm talking about the oriented Plateau problem. So ideally, what I'm actually going to treat is a slightly more general, much more general question. So in general, gamma will be, in our talk, an m-dimensional closed, smooth submanifold, where I actually should say also oriented, of either the Euclidean space, which I'm going to denote by Rn plus n. So in particular, n can be actually much larger than 1, or of some Riemannian manifold m. Okay, and ideally, by the fact that I want to solve it in the category of oriented surfaces, what I would really like is something like this. So ideally, I would actually like a minimizer is some equally smooth m plus 1 dimensional submanifold, say sigma, and what I understand as m plus 1 dimensional volume of sigma, this is the usual notion of area. So which in the Euclidean space, for instance, it could be the usual Hausdorff measure. And so that's the first point. And at the same time, the fact that actually sigma bound, that gamma bounds sigma might be simply understood that the boundary of sigma is equal to gamma in the differential topological sense. So what it means is that sigma is actually a submanifold with boundary, and gamma is the regular boundary of sigma. Of course, this also means as an effect that, for instance, Stokes theorem works. And if Stokes theorem works, that means that when I integrate over my surface or my n+1 dimensional submanifold sigma, some form the omega, so the differential of a differential form omega, then that's actually going to be equal to the integral over gamma of omega. Okay, so this is the ideal situation that I would like to have, but there's a drawback with this. So we're actually far from this ideal situation because of the following two questions. So first of all, such a smooth surface might not exist. Well, that's one point. And you can also raise the point, okay, maybe such a smooth minimizer exists, but if I allow slightly more non-smooth objects, maybe there is a non-smooth object which actually has less area than the smooth one. Maybe non-smooth objects can achieve less area. Okay, so of course you could say, well, whether non-smooth objects achieve less area or not, I might simply not care. And so I could actually ignore point two, but point one, you can't really ignore. I mean, there are really some situations in which if you look at the minimizing surface, which is spanning a given contour, and you look at them in the category of smooth surfaces or smooth submanifolds, there actually is no minimizer in that category, meaning that, for instance, if you take an infimizing sequence, you're necessarily converging to something which is non-smooth. So there's really no way out. You are forced, if you want a well-posed problem, a well-posed variational problem, to consider non-smooth objects. Okay. So now, if you're considering non-smooth objects in the category where I am, actually, so the kind of very successful theory is the one by Federer and Fleming in the 60s, which is predated by the Giorgi in the case of codimension 1. And this is the setting of integral currents, for which I just give you a very quick introduction. So one quick way of saying what an integral current is the following. So first of all, you just look at your at your set X, and say your set X is given by linear integral combinations of smooth surfaces with smooth boundaries. Okay, so here by surfaces, of course, I just mean n+1 dimensional surfaces. So by this, I mean that I might actually consider 2 times the surface sigma, for instance. So I could consider something like 2 times the surface sigma 1, and I don't know, 3 times a certain surface sigma 2. They have to be oriented. And then I define, I ask myself, so I first of all define what is the mass actually of this. So define the mass roughly as 2 times the volume of sigma 1 plus 3 times the volume of sigma 2. In this particular example, of course, more in general, you have a finite linear combination and you take the sum of the masses. And I just say here roughly because you should not do something silly like if your object is something like sigma minus sigma, which of course you would interpret it as the object being equal to 0, you shouldn't actually count the mass of this object to be 2 times the mass of sigma, but you should count it as to be equal to 0. Okay. And then, of course, the same you do somehow for the mass of the boundary. In this case, if your object is m+1 dimensional, here you're looking at m+1 dimensional volume. And then the same you do for the boundary, but by going 1 dimension less. And then you ask the following question. So what is the limit of a sequence of, say, objects sigma k, which are inside X, if I assume that the m+1, or let me actually use the notation with the mass. If I assume that the mass of sigma k plus the mass of its boundary is actually uniformly bounded independent of k. Okay, of course, what I understand as limit of such a sequence, even if you have, say, some compactness statement, probably you have to pass to a subsequence. So what I'm then sort of asking is, what is the closure of this set X over here under such a control? And of course, if I'm asking about what is actually the limit of a sequence of such sigma k, I have to specify in which sense I understand the limit. And I understand the limit in the following sense. So say a, So say a limit for me. So a limit is a linear functional L on the space of forms and I know that I can integrate over the sigma k is my form, and I just prescribe that when I evaluate the linear functional on this space of forms omega, so this is equal to the limit as k goes to infinity of the integral over sigma k of my form omega. Okay, of course I can actually apply abstract function analysis and like put say a general definition of sort of what is this space of linear functionals, which anyway they are called usually currents. And this is a linear space, and then it's actually rather easy to use classical functional analysis to show that the limit, at least in a certain sense, exists. But what I want to say by this question over there is, how can I really characterize them? So it's a little bit like saying, take the general space of distributions, take inside the space of distributions sequence of functions which are smooth, and assume that you have a uniform bound on the Dirichlet energy. So what is actually the limit of a sequence with such a bound? Well, of course, you can take a limit in the sense of distributions, but we know that a characterization of all the possible limits is given by the Sobolev space W12. And in a certain sense, the space of integral currents plays the same role for this nonlinear variational problem as the Sobolev spaces actually play for the Dirichlet energy. Okay, so the answer to this general question is given by Federer and Fleming in their foundational paper, and it's called the space of integral currents. And roughly speaking, any such limit L has the following structure. So if you wonder what L of omega is going to be, so L of omega is actually going to be some series with some integer coefficients ki, and I integrate over some sets psi I forms omega. And so the ki are integer, and the ci are inside some sigma I closed subsets of oriented C1 surfaces. So it's a little bit like the formal linear combination of surfaces, but what I allow you to do, I allow actually you to take not an entire nice smooth guy sigma I, but to take, for instance, a very fractal set inside. And so L has the following structure, and what is very important is that even the boundary of L has the similar structure, right? So of course, in which here I will have a sum, then I will have maybe other coefficients, and then I will have other closed sets, and now these closed sets will be inside some other gamma I. And of course, when I actually pass to the boundary, what will happen is that these C1 oriented surfaces gamma I will have one dimension less as the C1 surfaces sigma I. Okay, so that's good, but in a sense, of course, an integral Carlan could be a very fractal object. For instance, you might imagine you have a very nice disk, and then you start taking very protruding filaments, or you might actually take surfaces with corners, like for instance, the boundary of a cube. That would be a perfectly legal integral Carlan. And the Federer and Fleming theory actually says that in this category, so in the space of integral Carlans, there is a minimizer of the mass if you fix the boundary. And of course, you have to define the mass, and the way I would naturally define the mass of, for instance, such a current L would be to just say that the mass of L is going to be the series of Ki, and then I take the volumes of the sets Ci. And again, somehow this has to be like properly defined, because if I'm going to have some silly situation in which I have C1 and minus C1, so I'm counting actually the same surface with positive and negative orientation, I have a superposition, and I might actually have a cancellation. It's very similar to the situation that I explained you above, that if I have the surface sigma and I subtract the same surface sigma, actually I have to understand this as having mass 0. So that actually can be easily remedied, and I don't want to go into technicalities. Okay, so once you have actually this Federer and Fleming existence theory, you can ask how regular is the object that actually is my minimizer. Because, for instance, it's probably intuitive that if I have corners like in a cube, then that one is not a very good candidate for minimizing the area, because once I have a surface with corner, I can actually smooth the corner and possibly sort of have less length if I keep a certain boundary fixed, right? So this would be like a one-dimensional example in which if I take a curve which is non-smooth, then I can smooth out the corner and get a shorter length between 2 points, which actually is nice. Okay, so the basic question is, how regular is a minimizer? And of course, you have two different type of questions in here. So you have sort of the interior question. So in the interior question, you just like to say how regular is a minimizer away from the fixed boundary. And from now on, let us just put by convenience that the boundary is gamma. And so this is like interior regularity. And of course, you have a twin question, which is what happens at the boundary. And of course, when you ask actually how regular it might be at gamma at the boundary, you have to assume something a priori on the boundary that you have fixed. If you have fixed the boundary gamma, which is very rough, you cannot expect actually your minimizer to be good at the boundary. You will have to assume some regularity of the boundary itself. Okay, so assuming gamma, which is the given boundary, is actually nice. Okay, and you might wonder, why do I want to actually answer these questions? And one of the reasons is that if I want to extract some little geometric information, even some very silly, naive information about my minimizer, then I need to I need some regularity possibly to understand that. I mean, maybe it's not absolutely necessary, but usually it's a good way to actually extract further information about your surface, which is the minimizer. So let me actually come to the question of the talk, which is a question by Almgren. And this is a kind of guidance for like, you know, why we bother about this sort of regularity. And so Almgren back in the 80s asked the following question. So if gamma is connected, is the minimizer connected to? Okay, and it stands to reason that this actually should be the case. If your minimizer is regular, it's a very simple exercise. So if the minimizer is regular, the answer is yes. And that's very easy to understand. So if the minimizer is regular, say here I have my fixed contour gamma, right? If the minimizer is regular, then I can break it into the connected components. So let's say the minimizer is sigma. So let me write sigma as the union of the connected components. Of course, since gamma is connected, gamma must be the boundary of only one of these connected components. So say without loss of generality, I can say, oops, that gamma is the boundary of sigma 1. And of course, now, if gamma is the boundary of sigma 1, if you had more connected components like sigma 2, sigma 3, sigma n, they're just sitting over here and they're not doing anything. Sorry, so this is sigma 1, so this is going to be sigma 2, and then maybe here sigma 3. And since they are actually not doing anything, they're not contributing to achieving that the surface is the boundary of the surface is equal to gamma, I could just remove them and get something which has less area, which is not possible because your sigma actually must be a minimizer. Okay, so this is an interesting question, and let me just tell you that immediately that in fact back in his big regularity paper, so in 1980, Almgren gives actually the answer as a corollary of a very famous theorem of his, that this is yes in the Euclidean space, and I will explain you what happens somehow over there. But the question was open until our paper for a general Riemannian manifold. So, and now in our paper, so together with Guido de Philippis, Jonas, Hirsch, and Annalisa Massaccesi, so in 2018, we're able to say yes in a general Riemannian manifold. Okay, so let us go back actually to the regularity theory and let us see what is the big point. So there are actually two situations which are very different in the interior regularity theory, and which makes actually a big difference at the boundary too. So in the interior regularity theory, what we know is, so in codimension 1, the minimizer is regular except for a singular set of codimension 7 in the dimension of the minimizer. So if the minimizer, for instance, is a 6-dimensional surface, say in R7, then 6 minus 7 is equal to -1, and there's actually no singular set. Okay, and this is actually the combined effort of several mathematicians. Let me just mention the Giorgi, Almgren himself, Fleming, Simons, and Federer. And it's actually known since the 60s, 70s, essentially. In higher codimension, the situation is much more difficult, actually, and it's thanks to this fundamental paper by Almgren, which actually is a book back in 1980, that we know that the minimizer is regular except for a singular set of codimension 2. Singularities might have codimension 2. And in fact, I should say have codimension 2, and there are examples where they have codimension 2, and of course it's the same actually for the codimension 1, 2. So this theorem is optimal, meaning that there are examples where the singularities of hypersurfaces might be of codimension 7, but the theory actually tells you that they cannot have codimension less than 7, right? So both results are actually sharp. So that is for the interior regularity theory. And what happens actually for the boundary regularity theory? So for the boundary regularity, you have, first of all, a fundamental result by Allard, which essentially says a boundary point is regular if there is a convex barrier at the point for the minimizer. Okay, so but what I mean by this is that, so here I have my minimizer, which is staying over here. So say this is my minimizer sigma, and I have some, I should have say actually some uniformly convex barrier. So I have some uniformly convex surface, hypersurface over here, which is actually telling me that my surface sigma is all on this side of the convex barrier, and it touches, of course, the barrier at the point P. Okay, so now this is actually a very nice corollary. And the very nice corollary that it has, together with a very simple geometric consideration, is that if the minimizer is in Rn, there's always at least some point where you have a convex barrier, right? So in Rn, there is always at least some point with a convex barrier. And the reason seems pretty clear. Like if you have your boundary gamma, which is living over here, you can just take a very large ball So this is going to be, say, a ball of radius r, centered at 0. And if gamma is contained in the ball of radius r centered at 0, then it's very easy actually to say that any minimizer has to be contained inside, because if the minimizer goes outside, I actually can project it on the sphere and decrease the area. And then you can take the smallest ball that actually contains gamma, and such a smallest ball is bound to touch your surface gamma, at least at some point, right? So this is going to be kind of the smallest ball containing gamma, and that's actually a convex barrier for the minimizer. Okay, but in general, this convex barrier, of course, does not exist if you are in a Riemannian manifold, and the reason why it does not exist in a Riemannian manifold is because you don't know that you can foliate a Riemannian manifold with convex hypersurfaces. In fact, if the Riemannian manifold, for instance, is closed, this is certainly not the case. Okay, so convex barriers are, however, generally absent in a Riemannian manifold. So convex barriers are difficult to get, or impossible to get sometimes in a Riemannian setting. Okay, and so you might wonder what happens more in general, and what happens more in general is the following. So in codimension 1, there is another fundamental result, and that fundamental result is a result by Hard and Simon. And this actually dates back to the 1980, and it says that, in fact, for hypersurfaces, boundary points are always regular. So there is full boundary regularity. And this is an extremely nice result. It actually tells you that the boundary is in some sense better than the interior. So because at the interior, you might have actually singularities of codimension 7, but that cannot hold at the boundary. But for something like this in higher codimension, it was up to now an open question whether there is even just only one possible regular boundary point. Okay, and so up to our work, which actually was on the web, is on the web since 2018, in higher codimension, still open whether a single regular boundary point exists. And let me point out that, okay, so this is of course true in a general Riemannian manifold. In Rn, which is said, there is at least some boundary regular point by Allard's argument. But let me also point out that, of course, in general, if you have a complicated curve, there might be some point where you don't have any convex set which is touching it, which means that Allard's theorem will tell you that, for instance, in this example, there is regularity over here, and there is a regularity over here and over here, but inside here, there is kind of a big chunk not covered by Allard's theorem. Okay, and this is actually what we remedy in this 2018 paper. What we actually prove is that, in general, dimension and codimension there is at least a dense open set of boundary regular points. Okay, so let me give you a little bit an idea about what the subtlety is. So why is it actually much more difficult to prove regularity without boundary assumptions, and what is actually more advantageous in codimension 1 compared to higher codimension? Okay, so first of all, there is one example that you have to take in mind, which is the following. So if I take a boundary which is given by two curves, and let's say that I orient the curve in the same way. So if you take two curves which are on the same plane, so say here I have a two-dimensional plane which is sitting on R3, and here I have two curves which are which are oriented in the same way, the minimizer is going to be this area, this region, counted with multiplicity 1, and it's going to be this inner region counted with multiplicity 2. And an intuitive reason for this is simply the following. So you would like maybe to, say that you take actually the two disks to be kind of far apart. Okay, then it's pretty clear that this one is a minimizer. And now what happens if you actually slide the top disk towards the bottom disk? Well, you would at a certain point like actually to produce a competitor which maybe does something like this, right? So takes the lateral surface of something, maybe, I don't know, a catenoid or whatever. But what is happening is that this would be, in fact, a very good competitor if the two disks are nearby. And of course, eventually, when the one disk is going to touch the plane of the second disk, you're going to collapse on something which is a corona, right? This is what is happening when somehow the top circle actually slides down. But the problem is that when you look at this surface, its boundary is oriented in two opposite ways. So if I insist actually in taking the two circles with having the same orientation, then when I slide down the top circle, I actually end up by the top disk superimposing on the second disk in this area, which I have sort of taken much darker than the corona outside. Okay, so now by this example, what you have some sort of pretty kind of difficult to analyze situation in which if you take a point P over here, so this point P is actually sitting at the boundary, but when I zoom in and I look at the magnifying version of what is happening on this point P, so on this point P, what is happening is that I'm seeing one portion of the surface which is actually on the left, and it's counted with multiplicity 1. And then I'm going to see another portion of the surface which is actually lying on the right, and it's counted with multiplicity 2. And it's kind of very delicate in this situation, because in order to claim that you have regularity at the point P, what you really have to show is that if you're very close to this situation, then the two surfaces actually might have, do have to touch together, okay? So now this actually explains why when you don't have a convex barrier, the situation is much more difficult. Of course, on points where you have a convex barrier, so for instance, these would be, in this picture, the points over here. So when you have a convex barrier, right? So here in Q, you have a convex barrier, your surface has to lie all on this side. So they are all forced to be on this side. So when I actually zoom in around the point Q, there will be this convex barrier, which tells me that the surface has to be only on this side. It cannot actually cross over and go on to the left. And if I'm in such a lucky situation, I can hope that the analysis is much better. Okay, so now what happens in codimension 1? Well, in codimension 1, one of the things that you could actually bear in mind is the following. So assume you have, say, your boundary over here. So make this experiment. Assume you have your boundary over here, gamma, and this boundary is actually reached by kind of more branches of your surface, right? I don't know, something like this, okay? So of course, in order to have a situation like this, this is your boundary gamma, it has to be counted with multiplicity 1. So you must have something like multiplicity 1 over here, multiplicity 1 over here, and then of course this one is going to give you kind of a multiplicity -1, which is canceling with the other one, right? But you see immediately that something like this, if it's really drawn in this way, it's not really a good competitor. It's not really a minimizer, because you have a much better competitor, which is simply by taking this portion of the surface, say sigma 1, and this portion of the surface, sigma 2, and just check that sigma 1 union sigma 2 is a surface without boundary. So it's completely unneeded, and you can actually smooth it in this way and get a better competitor, right? Whereas, of course, the top surface, which I'm going to call sigma 3, is really taking the boundary, which is this guy over here. Okay, this is all good and nice, but of course, this is a situation in which I know a priori that I have such a situation. What happens if I just know that the two surfaces are kind of very close to each other, so that instead of making a corner, so instead of making a corner like this, right? So this would be the cross section. They just make a smooth joining, something like this, right? So this is going to be kind of the cross section in this situation. Okay, and now the situation in codimension 1 is so much more favorable, because if you think that your two surfaces over here are two graphs of the minima surface equation, then actually what is happening is that you would have two graphs of the minima surface equations. They cannot kind of cross in the interior. They join in gamma, but they also have the same normal derivative in gamma. And the Hopf boundary lemma is then going to tell you that that is not possible. The two surfaces would have to coincide. And of course, if the two surfaces would have to coincide, you are back to this situation in which, in fact, you are smooth, because you're just counting twice a portion of the surface on the right or on the left, and once the portion of the surface on the other side, right? So Hopf boundary lemma actually gives you a kind of the intuition of why you should be regular. Okay, so in higher codimension, especially so in the situation that we face, therefore, in our theorem over here, which is in general dimension and codimension, so it's not restricted to codimension 1. Of course, we don't have the Hopf boundary lemma, and it could perfectly be that at some occasional points, the surfaces actually on the left, they kind of touch. So that also tells you that you shouldn't expect to have full boundary regularity, and it's indeed possible to make examples in which there are singular points at the boundary. So Hopf boundary lemma does not come there, but of course you have some kind of substitution for that. A situation which would be really bad, and which you can rule out also in higher codimension, is anyway a situation in which two graphs, so Hopf boundary lemma just would tell you that two graphs cannot be on top of each other and have the same normal at some point P. But what you can actually draw as a conclusion in higher codimension by unique continuation arguments is that certainly, even in higher codimension, it is not possible that two graphs have the same normal at all the points on an open set, right? So the unique continuation tells you that if the normals of the two graphs actually they are the same on an open set, then by unique continuation, the two graphs have to be the same. So our Hopf boundary lemma forbids any point of contact So in higher codimension, unique continuation forbids an open set of points of contact. Okay, and that actually explains why, this heuristic explains why in our theorem what we can say is that regular points form a dense open set. The reason is that singular points of those type cannot have cannot form an open set, so they have to be meager. Okay, so that actually ends my talk.